Good morning, madam. My name is T. Pawan Kumar. Today I am submitting my CA2 assignment, and my topic is about to prove that the complete graph of five vertices is non-planar, and explaining Eulerian graph and Hamilton graph with examples. Before going to that, we want to know what is graph theory. Graph theory studies the relationship between objects called vertices connected by edges. It has applications in computer science, network design, and combinatorics. Today we will explore non-planar graphs, Eulerian and Hamilton graphs with examples and proofs. Complete graph of five vertices. The complete graph with five vertices denoted by K5 has every pair of vertices connected by an edge. K5 has a total of 10 edges because each of the five vertices connects to four others. This graph is crucial in understanding planarity and graph properties. Now we want to know what is planar graph. A planar graph can be drawn on a plane without any edges crossing. Kuratowska theorem states that a graph is a non-planar if it contains a subdivision of K5 or K3, 3. K5 is a key example of non-planar graph since it cannot be embedded in a plane without any crossings. Now we want to prove K5 is non-planar. According to Kuratowski theorem, K5 contains a subdivision of itself, making it non-planar. Euler's formula for planar graphs states that for a planar graph with V vertices and edges, V minus E plus F equals to 2. For K5, V equals to 5 and E equals to 10, which violates Euler's formula, confirming non-planarity. Eulerian graphs. An Eulerian graph has a path that uses every edge exactly once, called an Eulerian tribe. For a graph to be Eulerian, all vertices must have an edge degree. The classic example is a network of roads where a vehicle can traverse every street exactly once and return to the start. Example of an Eulerian graph. Consider a square with diagonals connecting all vertices, forming a complete graph K4. Each vertex in K4 has degree 3, which is odd, so K4 is not Eulerian. A better example is cycle with an even number of vertices such as hexagon, which is Eulerian. Hamiltonian graphs. A Hamiltonian graph contains a cycle that visits each vertex exactly once, called an Hamilton cycle. Not all graphs are Hamiltonian, but certain conditions increase the likelihood, such as high vertex connectivity. Finding a Hamiltonian cycle is the fundamental problem in a graph theory, which applications in routing and scheduling. Now we have to see the example of Hamiltonian graph. Consider a pentagon with one diagonal connecting two non-adjacent vertices. This graph contains a cycle that visits all five vertices exactly once, illustrating an Hamiltonian cycle. The existence of Hamiltonian cycles depends on the structure and the connectivity of the graph. Now, summary of the key concepts. K5 is a classic example of a non-planar graph due to its edge and vertex configuration. Eulerian graphs require all vertices to have even degrees, enabling a trail that covers each edge once. Hamiltonian graphs contain cycle that visits each vertex exactly once, which is vital in many practical applications and daily usage. Conclusion. Understanding the properties of K5 enhances our knowledge and non-planar graphs and graph embedding. Recognizing Eulerian and Hamiltonian graphs helps in solving real-world problems involving roots and cycles. These concepts are foundational in advancing the study and application of graph theory in the various fields. Thank you, ma'am. Thank you for giving this opportunity to me.